All right. Hi, everyone. My name is Catherine Shepard, and today I'm going to be going over your next lab with you. This lab is on light pollution and something that astronomers call seeing. And I'm going to try to help you understand what these two things are. And hopefully this lab will as well. So, as usual, I just have the lab pulled up here. Notice that in this lab, you have things called thought questions. These are questions where we just want to gauge what you're thinking, and there's no correct answer, so you won't be docked points even if say, I disagree with your answer. So don't worry. If you see a question like that, just answer it completely honestly. But you still need to answer it, or you won't get the points. So then, as usual, you have your definitions. These are really useful, especially if you don't understand things like star scintillation or seeing. So go ahead and read through those. And then the lab opens up with asking you to do kind of a mini experiment on your own. And this experiment mimics light pollution. So you just take like a little piece of paper, could be, a piece of your lined notebook paper, and you're going to take your pencil or pen and just poke a hole in it. Just one hole's fine. Then probably it's best to do this at night so that you don't have any additional light pollution coming in. But you'll take that piece of paper and you'll put a flashlight behind it, like the flashlight from your phone or something. And that tiny little hole with a lot of light coming through the back of it mimics a star. And so then if you place that across the room and you turn the lights in the room off, this is simulating what a star would look like at nighttime. You don't have a lot of external light like the sun preventing you from seeing the star. And so it should appear much brighter and more vibrantly. And then if you turn the lights on, it's simulating, say, being in a city where you're surrounded by streetlights, or being at daytime, or like twilight or dusk when the sun is just rising or just setting, and you can see some stars out in the sky, but not a lot. That's what these lights are simulating. So then, once you've done this experiment, the question 1 asks you, did your little light shining through the hole in your paper, did it appear brighter when the lights in the room were on or off, and why do you think that is? And hopefully that'll be pretty obvious to you. Just like thinking about if a star would appear brighter at night or in the day. And by star, I'm not talking about the sun. I'm talking about like Vega or Betelgeuse or something. Excuse me. So then question 2 asks, is this difference in brightness between when the lights in the room were on or off, is that difference in brightness the apparent or the absolute magnitude of the flashlight, or aka your simulated little star? That light that you're seeing, is that the apparent or the absolute? Now, to understand this, you need to understand what apparent magnitude is and what absolute magnitude is. And they're given in the definitions on the first page. Apparent magnitude is how we perceive a star, how bright we perceive a star to be as seen from Earth. So the distance to that star could vary wildly. If we're looking at the nearest star to us, it'll appear brighter than the furthest star we've ever seen, or even a star that's twice the distance away from us. So apparent magnitude means that the distance between the observer and your star varies. Absolute magnitude is defined as how bright your star looks, or how bright your object looks, because this applies to stuff like galaxies as well. How bright it appears to be from 10 parsecs away. And remember that 1 parsec equals 3.2 light years, or 9 trillion miles. So 1 parsec, again, this is kind of demonstrating that space is really big, so we can't always measure things in miles. So we have to measure things in light years, and even sometimes light years are too small. And remember, a light year is a measure of distance that describes how far light travels in 1 year. So 1 parsec is equivalent to 3.2 light years, and the absolute magnitude The distance between your observer and the object you're looking at is always set at the same thing. So that way you can truly tell how bright an object is. Because if you were looking at one of the brightest stars in the sky and say our sun, right? Our sun is like a mid-type star, it's a G-type star, and the brightest stars we've ever seen are O-type stars. And there are several types in between. I know that doesn't mean much to most of you, but if you were looking at the apparent magnitude of the sun versus an O-type star, they could look the same. The O-type star could look fainter than the sun because it's so much further away. But if you're looking at the absolute magnitude, the O-type star will always look much, much, much brighter than the sun. So, absolute magnitude, apparent magnitude, and it's just asking, so think about it. You're looking at this light that's in your room, and how bright it appears is changing based off of how much light pollution you're putting into the situation. So would that change in brightness be the apparent or the absolute magnitude if this was a star? So just think about it, give it your best shot. So then, number 3 is kind of just an opinion, there's no wrong answer. We just want to see how many of you have seen a really beautiful, bright, vibrant night sky. Like in this diagram here, on the left panel is the sky that you would see from Atlanta, and in the right panel is the sky that you would see if you were to, sit outside for a half an hour in a really rural area out in the middle of nowhere, like on a farm or something, with all the lights turned off and your eyes got super used to the darkness. You would see all these different stars. And if you were far enough away, you could even see the band of the Milky Way. So, we're just asking, have you ever seen this before? If you have, where were you? For me, I was at camp in California, which is where I grew up, years and years ago. So then we go on to talk about being able to see all these stars is not only beneficial for astronomers, but it's also beneficial for normal people. It's beneficial for me, even if I didn't want to measure stuff about these stars, to just be able to go out and look and see, wow, the universe is gorgeous. So we want to educate you guys on a resource that's out there, which is called the Dark Sky Parks. And these are plots of land that can either be public or privately owned. And meaning, I could own the land and say, hey, it could be a dark sky park. I could have it certified. And then I could allow people to come onto my property and view the sky and stay overnight. Or it could be publicly owned, like by the government or something. Anyway, you can go to this finder on this website, which I will open up for you guys. Wrong tab, but okay. So you can go to this Dark Sky Park Finder, and you can go to wherever you are in the world, zoom in, and find a dark sky park that is really close to you. So I am currently in North Carolina. Most of you, or others, are in Georgia. So where I am is kind of over here. So the closest dark sky park to me would probably be this one. And if you hover over it, it says the name, and this one is Pisgah Astronomical Research Institute. If you were in Georgia, in Atlanta, say, it could either be this one or the one in South Georgia, the Stephen Collins Foster State Park. Now, for this question, we just want you to write down the name of the dark sky park that's closest to you. You don't have to write down the one that's closest to Atlanta, just wherever you are currently. And you can see when I first loaded up this map that it gives dark sky parks that are located all over the world. So no matter where you are, you can find one. So then we want to get into, now that we've kind of introduced what light pollution does to how we see the night sky, we want to introduce why this is a problem for astronomers and how we get around this to do science. because we need to be able to see these stars to do any science with them. So you're going to look up these 3 telescopes, and all you're going to do is open up Google, type in the name, click on a link or two, find what the observatory name is called, and this could be, for instance, it could be at Apache Point Observatory, or it could be at Kitt Peak Observatory or something, and then where that location is. And you don't have to write down the address, you don't have to write down the exact location GPS coordinates. You can just write down city and state. That would be just fine, because all of these telescopes are located in the US. So now, the observatories that you just looked up are marked with red circles. And we'll be referring back to this image for the next few questions. So question 5, why do you think these telescopes are located where they are? So again, these red dots are way over here. This is a map of light pollution. So each of these bright dots is where a major metropolitan city is. So you can see that there are some really bright bands in California, and the East Coast from about the middle of the United States over to the east is really heavily populated with people. There are tons of cities, there are tons of people living there, so there are tons of light pollution. So just so you know, you will almost never find like a really well-known, renowned telescope or observatory on the East Coast. So why are these observatories located where they are? Not only think about light pollution, but you can also think about weather, right? The only observatories that can observe no matter what the weather are space-based observatories, so you get above the weather, or radio observatories, because radio waves penetrate everything in the atmosphere. They just pass right through clouds. But visible, ultraviolet, microwave, all of those, you need to have clear skies. And then on top of that, there's seeing, which I'll go over. But so think about weather, think about, rain, think about light pollution, and then why do you think all these telescopes are located where they are? Because they're all located in similar areas. So number 6, all of these observatories share one common feature in their building locations. Hint, they're built on the tops of the same kind of thing. What is it, and why would this be a benefit? So if you don't know or you don't have an idea, you can look it up on Google, probably. But if you think about it right, if it's a really hot day and you're driving down the road, you see these ripples all along the ground. And if it's really, really hot, and that's because the ground is heating up and then it's re-emitting all that heat in the form of waves. And so that disturbs the air super close to the ground. And so you get these massive ripples. So how do we get above that? So how do we get, what geographic feature does the world have that elevates something that gets us above that ground or lowermost layer, gets us above all that turbulent atmosphere, gets us above sometimes even the clouds, so we don't have to worry about weather. And it's a really common feature. It's all across the US and all across the world. What is it? And why would it be a benefit? I've kind of listed off a couple ideas about this, so if you were paying attention, you should know how to answer this. So then number 7, using the light pollution map and the building hint from question 6, where in the US would you go if you wanted to build a telescope? So would you choose to build a telescope on the East Coast, where you get a ton of rain, a ton of hurricanes, you have a ton of light pollution, a ton of people, there's not a lot of dark sky parks out there? Would you choose to build it on the East Coast? Or would you go into the desert where it's much drier and you don't get as much rainfall? And would you put it maybe up on the top of your answer to number 6 to get above all that turbulent atmosphere? Just, think about these things, and then where would you build a telescope? So now, number 8, we're going into part 3, ways that we can reduce light pollution as people. These two are just thought questions. What might be some difficulties when observatories are built hundreds of miles away from the nearest city, right? So think about emergencies. Think about constructing the observatory and transporting materials for that. Think about getting the observatory to run, right? We have people staying there overnight, so they need to have access to bathrooms, water, food. There needs to be some form of transportation to get you there and back. You need to have security. If you're out in the middle of nowhere, there's of course wildlife out there because humans haven't moved in and disturbed them. So we need some way to keep our observers safe. We need some place for observers who are traveling from other places to come and be trained at that telescope to stay for a few days. Think about all of that. And then you can also think about politics. What might be some issues with politics and land and reservations, because those places are generally really nice to build dark sky parks or telescopes. But generally they're protected, or there's an issue with coming in and building something on that land when it doesn't belong to you. So that's enough on that question. Number 9, thought question. What in cities causes the light pollution that requires the observatories to be built so far away? AKA, what in cities produces light? I can tell you right now, my computer screen is producing light. I can tell you right now that where I live, there's a giant light outside that we have no way of turning off that ruins my view of the night sky. We have street lights. We have planes flying around. We have cars driving around. Think about all that. So then, moving on. Like I mentioned, just really offhand briefly, lights, street lights. Street lights are a really major problem for observatories and light pollution. And this is a diagram that kind of illustrates that we don't have to choose to build a street light that produces the worst light pollution possible. And not only does it produce the worst light pollution possible, but it's actually much more inefficient, right? Because we're humans. We live on the ground. We don't float around in the air like aliens. So why would we need a 6-foot radius of a sphere that is not just illuminating the ground where we're walking? Really, the one on the far right, the best one, is best for astronomers because it contains all the light down, so it's not polluting the night sky. And it's best for energy conservation because you don't have to pay to have this much, much, much brighter bulb that kicks out all this energy so that you would have the same amount of illumination on the ground as you would have if you had a less powerful bulb that was just contained. So there's a lot of things we can do to help this problem. So just as an activity, just quickly set this lab aside, pop outside, and take a look at a street light where you live. And this could be if you're in an apartment building, what's the light on the side of your building? Or if you're on a house, what's the street light outside? If you don't have street lights, say, I don't have street lights. And then if you want to, when you're going into school or work, you can look at the streetlights that you pass by in the city because I can guarantee you there will be some there. And you can write that in here as well. So then number 11, would where you live be a good place to build an observatory? For instance, I live up in the Smoky Mountains of North Carolina, so I would put no. Because even though it's on the top of a mountain, I get a lot of rain, so the weather is terrible, and we have really strong wind gusts, which are also dangerous. And there's a lot of light pollution because I'm on the East Coast, so I would put no, taking all those things into account, not just the street lights. So then part 4, seeing, finally. Seeing is a way that astronomers measure how turbulent the atmosphere is. And a seeing value of 0 is impossible to get, but is the best. And then the higher the value of seeing, the worse off you are. So I commonly go observing. I'm actually observing tonight. And whenever I observe, the operator measures the seeing for me and reports it to me, and I can make a note of it in my observation log. And I can say, seeing's really bad tonight. It's like 2 arc seconds. Or I can say, seeing's pretty good tonight. It's 1 arc second. And this is just a measurement of how blurred something is away from what we expect it to be. So, and you can think about turbulence as when you're riding in a plane and you experience turbulence and you get kind of jostled around in your seat, or you might, spill your drink. You never want to be using the bathroom on a plane when you're going through turbulence. It's very uncomfortable. That turbulence is exactly what I'm talking about. So this is an example of what different values of seeing would do to something that we're observing. So this is just an observation of Jupiter taken with the same telescope, with the same equipment, with really good seeing on the left-hand side and really bad seeing on the right-hand side. So you can see that for planets, seeing just kind of blurs everything together. But you'll see something different for stars. So, number 12, what phenomena influences the seeing of an object? Think of what we're looking through when we observe from the ground. So, right, I said we have heat waves on the really, really close to the ground of Earth when it's really hot. You go through turbulence, which are waves in the upper atmosphere when you're flying in a plane. But you wouldn't experience any turbulence in space because there's nothing there. Turbulence, and therefore seeing, is caused by the very thing that keeps us alive. Not the sun, but the other thing that Earth has that allows us to breathe and keeps us from getting roasted alive by the sun's radiation. So what is that? Just name it. Number 13, we know that atmospheric turbulence influences seeing. What is atmospheric turbulence and what causes it? So this is pretty straightforward. We're just asking for a definition of atmospheric turbulence. What is turbulence? Is it an alien shooting a laser at us? Is it waves? Is it raining cats and dogs? What is it? And then what causes that? Is that caused by heat? Is it caused by the very motion of the plane flying through the atmosphere? What is it caused by? So then number 14, how would turbulence affect how we see an object in space? Hint, think of what happens to a plane as it flies through a turbulent air pocket. So exactly what happens to the plane? Does it fly straight through and is unaffected? Is it jostled around? Is it completely thrown off course and the pilots have to make a really quick correction so we don't all crash into the ground and die? What does turbulence do to a plane? It does the exact same thing to light. Because as we're looking at an object, we're looking at the light that we see coming from that object or being reflected off of that object. So, what does turbulence do to light? Number 15, how would turbulence affect objects that are close to us, such as an asteroid in the solar system, differently than objects that are much further away, like stars? And this is getting at the really key point that is difficult to understand sometimes, which is that turbulence will not affect different sized objects the same. So, and right, size in space is all dependent also on distance away from us. So even though a star is much bigger than a planet, it's much further away, so it looks to be much smaller. So, how would turbulence affect objects like a planet or an asteroid if we're looking at it like with binoculars or with a telescope, differently from a star that is millions of miles away versus a planet that's just 1 million miles away or something like that? Which would be more greatly affected by atmospheric turbulence, a star or a planet, and why? So think about how sensitive something can be depending on its size, right? So if you think about marbles, I know I loved to play around with marbles when I was a kid. If you have a really big marble, it's really sturdy. It's hard to knock out of the way. And if you have a really small marble, it's much lighter. It's much more easily disturbed, right? So if you're playing that game where you have to like flick the marbles and you have to get as many of your marbles into a circle as you can. If you have a big marble in the circle and a small marble in the circle, that big marble will be much more difficult to knock out of the circle versus the small marble. Because the small marble, you just have to hit with a tiny bit of force and it will go flying off. Whereas the big marble, you have to hit it with much more force to get it to move out of the way. Turbulence kind of does the same thing. So, just based on that description, what do you think would be more greatly affected by atmospheric turbulence? A star, which is much, much smaller, or a planet, which is much, much bigger? And why do you think that is? And this is all leading up to what we're trying to get across in this section, which is why do stars twinkle, but planets do not, right? So whenever we draw stars, we draw like a 5-pointed figure, and those points are a star twinkling. We even have a song called Twinkle, Twinkle, Little Star. We don't say Twinkle, Twinkle, Jupiter. Planets, like in the seeing image that I had pulled up earlier that's in this lab, this one, the planet's not twinkling. It's just getting blurred. So why do stars twinkle, but planets only get blurred? And this is really the big takeaway question from this lab. This is what we're trying to get across. So this is also a note in that if you have trouble with these two questions, you don't understand what I'm talking about with the marbles and stuff, you can do an experiment that will hopefully help you understand this. And this is just, you can fill your kitchen sink with some water, or you can fill your bathtub with some water. Or if you don't have either of those, you can take like a baking tray and fill it with some water. And then you want to take like a plate and then a coin, maybe like a penny or a quarter or a dime or something. And you put both of those in your tray of water. And then you take your hands and you splash around in the top of the water. And what this does is it acts as the atmosphere, right? The atmosphere is what we're looking through when we observe stuff. So we would be looking from Earth. The water is the atmosphere, and the two objects, the coin and the plate, are the planet and the star that we're observing. So which one is more, the image that you're seeing, which of those images is more disturbed by your splashing around in the top of the water? Yeah, so then this note just says, observe how each object looks through the turbulence, think about what causes the difference in appearance from our perspective, and then reconsider the questions. And we have a nice little diagram here that you can zoom in on, and you can see that with the star, you have a really narrow beam of light coming through, and then Earth's atmosphere really messes it up, and we get a really distorted image. Versus Saturn, which is much larger and much closer, has a much larger beam of light coming through the atmosphere, and so it's not disturbed as much, if at all, and it's disturbed in a different way. So, moving on, we're going to move outside of our solar system. And you're going to try to measure the seeing of these objects. So here we've provided a link leading to an online ruler that we would like you to use. And this ruler should automatically calibrate to whatever size your screen is. I'm using a MacBook Air, like a 13-inch screen, something like that. So you click on the link and it brings you to this page. And it'll have a little pop-up asking, are you using this format computer, this width, blah, blah, blah. So then you can click the blue button here that says drag it. And you'll get a nice little pop-up of the ruler. So then you want to take that pop-up and move it onto the desktop or just on top of the lab that you're using. And what you're going to do is you're going to take this ruler and you're going to bring it down. Do not resize it at all. It's okay if it moves off the end of the page. You're going to take this ruler and you're going to line it up as close as you can with the edge of the ruler, which is 0, being lined up with the edge of the red line. And then you're going to try to measure where this red line hits on the ruler. Now, your measurements might get a little distorted if you have your document zoomed in too far. So just leave your document zoomed in at 100%. That's it. And measure from there. So where I am, it looks like I'm getting really close to 1 inch. Sorry, no, not inch. These are in centimeters. So I'm getting about 1 centimeter, if not like 0.95 centimeters. You do not have to get super specific. I would say, 0.9 to 1 centimeter, because I can't really tell the difference without zooming in. And so then you just want to come down and do the exact same thing with all of the others. And as you do this, you're going to write your measurements down in table 2, even for the standard. So for the standard, I would put 0.9 to 1 centimeter. And that would be my answer. And then, number 18, the very last question of the lab, compared to the standard image, which of these images, A, B, or C, has the best seeing and which has the worst seeing? And remember that the best seeing is the lowest value and the worst seeing is the highest value. So, and you can just write the best seeing was A and the worst seeing was B, whatever it turns out to be. And that is it. That is the end of this lab. You don't have to use a simulator for this. We only had 2 links that you had to click on. I hope that my explanations were helpful. I tried to keep this really short. Please, if you have any questions, feel free to email either me or Asmain, and we would be happy to answer any questions that you have, and or come to our discussion sections throughout the week. And I hope to see you there, and good luck. Bye, everyone.